This Zoom session is being brought to you by the fractal Bullseye Bubble Fire. All right, for today, we start doing some serious trigonometry with the law of sines. This rule will prove to be useful to solve angle-side angle problems, angle-angle side problems, and side-side angle problems. Here we go. Start with a triangle. The angles alpha, beta, and gamma with sides A and B, and drop this perpendicular height h. Now, h over b is the sine of alpha. H over a is the sine of beta. We write that here. So by transposing the b and the a, we get that h equals b sine alpha and a sine beta. Then transposing the sine beta and the sine alpha, we get that b over sine beta equals a over sine alpha. Now, okay, this is between a side and the opposite angle, a side and the opposite angle. There's a third side and a third opposite angle, and there's no reason not to include that in the equation. In fact, there's a sort of a general symmetry rule, which says that if you have a trigonometric identity, then if you swap the labels alpha to beta to gamma to alpha, and a to B to C to A, that three-way switch just changes the labels. It doesn't change the sides. So therefore, the identity would be true under that swap. Therefore, if you include C over sine gamma in this triple identity equality, then it's still valid. So in general, A over sine alpha equals B over sine beta equals C over sine gamma, side over sine of the opposite angle. They're all equal. That's the law of sines. Now, from this, we can derive various identities. For example, you can solve for A. Transpose, it would be C sine alpha over sine gamma. Or transpose sine beta and gets B equals C sine beta over sine gamma. So if you had all three angles, alpha, beta, and gamma, and the side C, then you have the other two sides, A and B. Angle, 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 side equals side, side. Now this requires all three angles, but that's all right. If you have two of the angles, then the third one follows. Gamma equals 180 minus alpha minus beta. Basically, each angle is 180 minus the other two. Therefore, if you have two angles, then you have three angles. If you have two angles on a side, then you have three angles on a side and the other two sides. If you have an angle side angle, then you have three angles on the side, so three angles on the three sides. Angle, angle, side. Given an angle and a side, find the other angle on the other two sides. That happens. Angle, side, angle. Given an angle, a side, and an angle, find the other two sides and the angle. Again, by this method. So, for example, here we have a triangle. We're given angle beta is 25 degrees. We're given side C is 12.0. And we're given this angle alpha is 45 degrees. What's angle gamma? What's side A and what's side B? We always start with the angle. Gamma is 180 minus the sum of the other two. 180 minus 45 minus 25. That's 110 degrees. Okay, so we have all three angles. Now, side A is C sine alpha over sine gamma. Remember, C over sine gamma transposes sine alpha. Plug in the numbers, 12.0 sine 45 over sine 110. It'll be about 9.029. Side B, remember C over sine gamma transposes sine beta. C sine beta over sine gamma. And the numbers 12.0 sine 25 degrees over sine 110. B is about 5.397. So this was an angle side angle problem. Here's an angle angle side problem. Given two angles, A and beta, alpha and beta, and side A, opposite angle A, alpha. What's the third angle gamma? What are the other two sides B and C? All right, now, as before, we find the third angle gamma by subtracting 180 minus 47 minus 23. That comes out to gamma is 110 degrees. So all three angles and one side. And B will be A sine beta over sine alpha. All right, 51.2 sine 23 degrees over sine 47 degrees. about 27.354. C will be A sine gamma over sine alpha, 51.2 sine 110 over sine 47, about 65.782. All right, the book had this example, a kind of perspective problem. This is, I'm not showing the mountaintop that this cue is on, but here at one place, you look up and you crane your neck at an upwards at an angle of 25 degrees, an angle of elevation of 25 degrees. Then you back off 1,000 feet and you crane your neck up to see it at an angle of only 15 degrees. Then the question is, what is this distance PQ, given we have this angle here, 110? Well, okay, first of all, this angle here, RPQ, is the supplement of 25 degrees. So it's 180 minus 25 degrees, or 155 degrees right here. And this angle at Q, PQR, will be 180 minus 15 degrees minus this angle of 155 degrees, 10 degrees. So we have 15 degrees here, 155 degrees here, 10 degrees here, and this side here is 1,000. This is the side we're looking for, PQ. PQ over sine of the opposite angle, 15 degrees, equals 1,000 over sine of the opposite angle, 10 degrees. Here, PQ over sine 15 equals 110 over feet over sine 10. Transpose the 15, so you get PQ equals 110 feet, sine 15 degrees over sine 10 degrees. After a bit of calculation, that's 1490.5 feet. I go to one decimal place, so that's really excessive accuracy, given we only have this down to unit accuracy, but let that be. Now we have what I prefer to call the side-side angle problem. I'd rather not call it an angle side-side because that's inadvertently humorous. I also call it the pendulum. And incidentally, we have an extra credit set about that. I'll turn to that right after this. So we have an angle here, a side here, and a side here. What are the other two angles, and what's the third side? Now, B over sine beta equals A over sine alpha. So therefore, after a bit of algebra, sine beta equals B sine alpha over A. Well, we're given B, we're given A, we're given alpha, so we can get sine beta. Now the problem is this can be quantity, it could be bigger than 1. If it's bigger than 1, well, there is no angle whose sine is bigger than 1, then there'd be no solution. I think of this as the problem called the pendulum, because I think of this as like a pendulum at the end of a cantilever. Here the cantilever is raised up so high that the pendulum clears the floor and never touches down at all. Therefore, there's no solution to this problem. If B sine alpha over A is 1, then there's only one possible value for beta, namely 90 degrees. The pendulum scrapes the bottom, just touches down at a 90-degree angle, and there's one and only one solution. If, on the other hand, B sine alpha over A is less than 1, then this beta can be 2 possible values, and the pendulum touches ground at 2 places. So there'll be 2 solutions. Arc sine, where beta is arc sine of B sine alpha over A, or where beta is 180 minus arc sine of B sine alpha over A. These 2 values, an arc sine and 180 minus the arc sine, have the same sign. This third case, where 2 solutions, called the ambiguous case. That's what so therefore this is this problem is sometimes called the whole problem. The pendulum or side-side angle is sometimes called the ambiguous case. So for example, let's say that B is 5, C is 3, and beta is 100 degrees. What are A, beta, and gamma? Now, here we're given B and beta and C. B over sine beta equals C over sine gamma. After a bit of algebra, that's sine gamma equals C sine beta over B. So we plug in the numbers. 3 sine 100 or 5, which is about 0.59088. Now, okay, so we want to find an angle gamma whose sine is 0.59088. So here I draw a unit circle. We go up a distance 0.59. This angle is a solution for gamma, but so is this. So this angle here is arc sine of 0.05988. This supplementary angle here with the same value of sine is 180 minus that arc sine of 0.59088 and so on. This one gives you a value of 36.22. This one gives you a value of 143.78. So there's two solutions. Well, maybe there's two solutions. And so here's what we do. We make a table with two solutions. We already know beta is 100 degrees. We already know gamma. We already know that B is 5 and C is 3. Okay, we put these numbers here. 36.22 degrees goes here. 143.78 degrees goes here. Now, having gotten beta and gamma, we find alpha as 180 minus beta minus gamma. In this case, 180 minus 100 minus 36.22 gives you 43.78. This one's odd, however. Here, you try 180 minus 100 minus 143.78, we get a value of negative 63.7, is that a 5 degrees? Well, not possible, you see, that's impossible. You can't do that at a negative angle. What that means really is that the pendulum is so long that it touches ground behind the cantilever. C was bigger than A. B, the opposite side, was bigger than C, the adjacent side. So in this case, we can rule out the second solution. Sometimes that happens. Sometimes in this case, when the opposite side is, when the pendulum is longer than the length of the cantilever, this happens. But in any case, here we have a possible solution. And these value the angles. Here's B, here's C, and then we find A as B sine alpha over sine beta. And plugging in all these numbers here, we get about 3.513. Here we have A equals 2, C equals 1, gamma is 100 degrees. So we're given A and C and gamma. C over sine gamma equals A over sine alpha. After some algebra, you get that sine alpha equals A sine gamma over C. Plug it in to sine 100 degrees over 1, which is about 1.9696, which is bigger than 1, and there is no such angle alpha. So in this case, there is no solution. So okay, here's a case with no solutions. Here's a case where one of the solutions fails because the pendulum is longer than the cantilever. Often you'll get both solutions, and I will require an answer in this form, where you have a table here with two solutions on it. Before I go on, let's see. I was mentioning that I have a extra credit set in the modules. Let's take a look. It's down here. And by the way, I recommend, we have all these others. Stereo and Trihydrate are versions of the law of sines. Here's the pendulum rule. Click on it. You will see a several page document talking about the pendulum or side A angle or ambiguous case. So I go through this whole thing, give it an angle, a side, and a side. What are the other angles? What's the third side? And I mentioned there's no solutions where the pendulum misses the ground. One solution where the pendulum scrapes the ground. Two solutions where the pendulum touches down twice. And if B is less than A, the pendulum is longer than the cantilever, then one of the solutions fails. So there's back to one solution. This goes through a different formula for it. A formula rather like the law of cosines, which we'll be covering next time. And I go over it and get this formula, rather different from the one we saw before. It has the virtue of being not having to invert a sign. So it gives you through two values of C and the near one or the far one, the pendulum scrapes down. And that's called out the pendulum law, and from that we find the other angles, etc. Oh, to find the other angles given the sides, well, from the pendulum law, I derive something called the law of cosines, which we'll be covering next time. And from that, I derive what I call the law of arc cosines, which also I'll cover next time. So there'll be pendulum law, 3 versions, law of cosines, 3 versions, law of arc cosines, 3 versions. And I get work through a couple of examples. Here's a case where there's no solutions. Here's a case where there's exactly 1 solution. Here's a case where there's 2 solutions. And here's a problem. Here's a problem set with, I believe, 8 problems, 8 problems, 8 points. For each one, I give you room to put 2 solutions. Though some of these have no solutions and some of these have 1 solution. So, okay, that's how that one works. So that's something that you can do, pendulum law, as an extra credit set. Just a second. Modules. Back to where we were. Just a second. Next time we will cover section 4.2. Oops, sorry, we already did that. My apologies. Next time we'll cover 4.3. Here we go, excuse me. The law of cosines. So here this is. I just saw it, but here it is again. Law of cosines in 3 versions. And here's the law of arc cosines in 3 versions, which the law of cosines from a side and an angle on a side, you get the 3rd side. From the law of arc cosines, you get from all 3 sides, get all 3 angles. And we'll work on some examples of that next time. Okay, that should do for that. All right.